All right, so in order to solve these beams, you have a few examples. Look at the few examples that you have. The important thing is to solve a beam like this, you look at your boundary conditions. So for example, I have a cantilever beam, Euler Bernoulli cantilever beam, so I know which differential equation I'm solving. I have Young's modulus, beam is 5 meters long, rectangular cross section. The height of the beam is 0.5 meter and the width is 0.25 meters. I have 125 kilonewton applied at the free end. And you're required to draw the contour plot of sigma on 1 and sigma on 2 and the von Mises stress. So in general, when you do the beam analysis, you usually stop at finding the bending moment and the shearing force, which is when you design a beam, you actually design the beam based on the stress. And so it's important to look at where the maximum stress is and where the maximum von Mises stress on a beam. So to solve the differential equation, it's EI d4y by dx1 power 4 is equal to 0. I need 4 boundary conditions. The boundary conditions are either y, theta, moment, or shear. So what do I know here? I know that y is 0 and theta is 0. And what do I know here? I know that the moment is 0 and the shear is equal to positive 125. Why did I say positive? It's because this is the positive shear, this is the positive moment, and this is the positive Q, and this is the positive Y. So this is solve this differential equation, find Y. Once you find Y, you know everything about your beam because you know that the stress or the moment. So you know that the moment is equal to, once you find Y, you know the moment, you know the shear, and sigma on 1 is equal to negative m x2 divided by I, and sigma on 2 is equal to negative shear multiplied by Q divided by IB, where Q is the moment of area. So if I'm interested in the shear at this point, I draw a line, I look at this area, I consider the moment of this area, and I consider this width B, and Q is equal to moment of area. Put Q and put I, put B, and find my shear at this particular point. So let's understand just those two equations. Sigma on 1 is equal to negative moment. What's the moment function of? X1 or X2? Or both? Just X1. X2. And usually, let's say I is constant. So sigma on 1 varies according to X1 and according to X2. What about sigma on 2? V is also a function of X1, and Q is a function of X2 divided by IB. Again, function of X1 and function of X2. Both are function of X1 and function of X2. You get a distribution of the stress. This is sigma on 1, and this is sigma on 2. This is the displacement function, or the displacement vector of the beam. Sigma on 1, as you can see, increases. Here, the maximum, and here is the maximum, and here is the minimum, and this is m multiplied by c over I, negative m c over I. And because the shear is constant for this particular problem, you get the distribution of the shear. Now notice the difference here is that the stresses, sigma on 1 is maximum when the shear is 0, and is 0 when the shear is maximum. So when you look at the von Mises stress, the von Mises stress, it does not differentiate between tension and compression, and that's why you have numbers. You have the number here and the number here, they are the same. And so the von Mises stress at the top of the beam is equal to von Mises at the bottom of the beam. And because I have sigma on 1 and sigma on 2 at every point, I can find the principal stresses at every point. The principal stresses at every point will depend on the stress matrix. The stress matrix here have components, sigma on 1, 0, 0, 0, everything else is zeros. Because it only has sigma on 1 as a component, it doesn't have sigma on 2. Then the eigenvectors are basically E1 and E2. The stress matrix at this point, sigma on 1 is 0, but I have shear stress. The only stress I have is shear stress. And so the eigenvectors are aligned at 45 degrees. And in between you have an alignment according to, so the eigenvectors are according to the interaction between sigma on 1 and sigma on 2. So in the middle, 45 degrees, aligned at 45 degrees. At the top, they're aligned with our basis vectors. And so, as you see here, these are the directions of the maximum principal stresses. I'm just going to scroll to the bottom here and show you the directions. If you do it in a finite element analysis, the directions of the principal stresses. This is the directions of the maximum principal stresses. The maximum principal stresses at the bottom are directed in this direction. This is a simple beam. And so if you were designing this, if this is a concrete beam, you put your steel bars at the bottom here. Closer to the support, that's when the bending decreases and the effect of the shear increases. And that's when you start seeing that the principal stresses are more aligned with an angle. And so if this would crack, if this concrete beam would crack, it would crack perpendicular to those principal stresses. And that's why you need what we call the shear studs, or shear reinforcement. And in the past, when I studied concrete beams, we used to put the shear studs or the shear reinforcement in this direction. But I think now it's easier for manufacturing and for everything that the shear studs are more oriented in this direction. It's easier for manufacturing. So there are a few examples in the in this chapter, but they're all the same, basically solving the differential equation, finding the moment, finding the shear, and then drawing the control plots of the stresses and the strains. So I think this is fine for today because you guys have to go and study for the midterm. I don't want to add more to what you already are dealing with. So I'm not going to add anything. I was going to talk about the energy, but we can start this next time. But remember, next time it will be probably, I'll take the full, I might take an extra 10 minutes or so. But we're on track. I might move all the assignments dates 1 week. So right now there's no assignment due next week. Depending on how much we cover next week, I might move, there might not be an assignment due the week after. So we'll see. We'll see what we cover next time. If we finish what I need to finish in the next lecture, then we're on track. If I don't finish it, then we're just going to move everything by 1 week. Because we already have one lecture that's revision, but in fact, the last two are actually revision. Because usually plasticity, I talk about plasticity and then at the end I ask, do you guys understand? And then we just repeat again the last lecture. So we actually have 2 revision lectures. All right, so I guess that's it.